Now, what about stick slip? Actually, the terminology is coming from stick and slip. Okay, when you play a violin with a bow, actually you're playing a game between friction and the force that is acting on the string. Okay, and that mechanism is playing many times at a second. Here the game is a little bit different, but terminology is the same. So stick, friction is winning, then it's losing and slip. Each time that we have a slip here, we can call it an earthquake. It's not radiating in a very efficient way seismic waves, but every time that you have the slip, actually, so stress is building, we have a game of building stresses here. Okay, yeah, very welcome, so we can close the door. That's the game. Now in this cartoon here, everything is simple because we have the friction due to, for example, some sandpaper, and the grains are deciding the friction flow. It is very simple in principle. Actually, it's electromagnetic forces if you want to go to a microscopic scale. But it's simple. And then we have a force, an external force that is loading the stress. Of course, if no force, the system will stay in equilibrium, in a static equilibrium, so no slip. But if we exert a force, then okay, the game is playing. Now, what about, well, everything is here. But again, if we assume to know all the details of this process here, we can try to make a sort of a prediction. So if we know the force, if we know the sandpaper, okay, we will know how much and when the slip will occur. Of course, that's not the case in nature. But the game is practically the same. So from a dynamic point of view, that's the context, framework, what we have to study, and we are going to try to understand the kinematics. But for today, this is the sort of a dynamic vision of the problem. Now, as I told you, in principle, the law is very simple, and it is called elastic rebound. So stress is loading, friction is playing, friction is losing, slip. Suddenly. Well, what does it mean suddenly? In a very short time. We have seen in the previous lecture that for a mega earthquake, let's call it magnitude 9, we're going to define what is magnitude, but for a big earthquake, actually, it's not so sudden. For example, for the Toku event, 2 minutes were necessary for the rupture to start, to propagate the rupture, not the waves. Waves are going to be propagated, of course, but the rupture was starting, propagating, dynamically evolving, and then stopping. It's sudden, 2 minutes. It's nothing compared to other time scales. Okay, in a very simple case, we can imagine, whoops, why it's not playing here? It was playing, okay. So stress is increasing. You can imagine also to have 2 combs, okay, and you exert a force, and then you will have a slip. That's the time when the waves are going to be excited and they are going to propagate. Following the laws that we tried to understand during the wave physics course. So the P waves, the S waves, but you do remember what's going to happen if we have a surface. And speaking to you free, what's going to happen if we have a free surface? We have reflections. If we have a layer, we can have multiple reflections. So phase waves, lob waves, Rayleigh waves, you do remember, okay? So all the possible wave trains that can be propagated. But the source, from a dynamic point of view, can be imagined to be something like that. So stress is going to be accumulated, friction is playing, and then it's losing, and then we have an earthquake. Now, at the end of the story, we will try to understand what is the balance that we have to study to understand when an earthquake is going to happen and why. And we will try to describe that. And then on the next lecture, we will try to study how to say, the kinematics and the properties. This is a nice picture that is coming from the textbook that I suggested to you. Okay, have you been able to collect this triangle session? I think you have some copies here. What about you?
No, I didn't find the book, but I will.
There should be a copy at both at the library at our department, but also at the Central University, the technical library. Okay. Otherwise, there are some copies here, as far as I remember. It's not difficult to find it on the web. Okay. So these pictures are coming from that part. So faults. It's not my cup of tea. I'm not studying faults because I'm studying what faults are causing, so wave propagation, but you can imagine that we have a place where we have blocks. Tectonics are exerting the forces, friction, and then we have a sudden release of energy. That's the earthquake. Of course, faults are not isolated systems. They are a system, so they are talking each other in some way. There was a very nice paper published on Nature a few years ago that was called, I don't know if it was published by Stein, but it was called Earthquake Talks, okay? Something like that. So we have systems here. Now, please do remember that to have an earthquake, we need something that is brittle. If everything is ductile, so let's imagine that the pressure and temperature conditions are so strange that all the system is ductile, we have no earthquakes. We're flowing, just flowing, okay? So that's the difference between a fault and the shear zone. In both cases, we have dynamic forces acting on the system, but in this case here, we have just flowing. So there is a strange difference between a fault and the shear zone that is decided by rheology. So our system is going to behave when we apply deformation or stress and deformation, okay? You do remember what is the difference between stress and deformation? For example?
Stress is just reacting the force in the material, and the strain is the elongation or deformation.
Okay, you're using this mimics, but please remember that deformation is also shear deformation, okay? So we have compressions, rarefaction, and shear forces. Okay, please do remember the units. Stress is like pressure, that is a tensor, and strain, it is a pure number, okay? Good. Okay, if strain is occurring without jumps, we have a shear zone, like in this case here. Everything is decided by rheology. And rheology actually is the physical behavior of the system when stress is applied. And please do remember, we will not enter into these details. Maybe with Karim, you will enter into these ones. But remember that pressure and temperature and composition, of course, they're very important. So to have an earthquake, to have a fault, to have a fracture or something like that, we need a brittle system, not a ductile. Please do remember the time, okay? Because the time window over which a stress is applied is deciding also rheology. So pressure, temperature, and time. Because, for example, if I stay on this table for 20 years, maybe I'm not that heavy, but in some time it's going to be deformed. But if I knock on that, very suddenly I'm going to excite waves. So we have a mechanical reaction on very short time scales, and some reaction over years. So we have a permanent deformation. Okay, what's next? Okay, this is a wordy slide, you can go there. That's the keystone for today. Now, what about the first panel? Well, you should know it. We should know it. Because actually, the first course of wave physics was in this regime here. Everything we did in wave physics was starting, if you do remember, from Hooke's law. Rubber chalks. Oh, thank you. So we developed pretty much everything like this, very simple. We have a force, we have a deformation. And the deformation is linearly proportional to the force. Later in the course, we generalize the F with stress, we generalize the X with strain, we generalize K with the generalized Hooke's law. If you do remember, it was a nightmare because then we thought, okay, guys, we have to study 81 components because it was a fourth order tensor. But since we were lazy people, we said, okay, no, it's homogeneous, isotropic, just 2 components here. And we have lambda and mu, lambda parameters, that are related to velocities. Okay? And if you do remember, density here is playing the role of inertia in some way. Is the amount of mass per unit of volume. Velocity constants. If we consider a pure ideal fluid, mu is vanishing, and we are left just with sound waves. If we do not consider an ideal fluid, but a solid, mu is a rigidity modulus, and it's deciding how a system is reacting to shear forces. What's next? Okay, please do remember mu, because as I told you in the first prequel lecture, mu is entering into maybe the most important definition of this part of the course, that is seismic moment, rigidity modulus, because we are going to study shear dislocation. That's why mu is there. Okay, so that was wave physics. But then we have to imagine that every system, beyond some limit, will not behave in a linear, elastic way. Maybe it's going to break, like a chalk. Or maybe it's going to behave in a plastic way. So we are going to have a permanent deformation. Now, please also do remember that in the Hooke's law, like this one, there is no time. It's immediate. We act, immediately we have a deformation. We remove the force, immediately we will go back to the equilibrium. There is no time there. But if you consider a plastic system here, so you go beyond the initial linear behavior and you imagine to remove the stress, okay, you will not go back to the equilibrium. You will have an area here. Now, when you have an area in force and displacement, or stress and strain, can you guess what it is, an area there? Let's imagine that we have F and X there.
It's energy.
What is a force times a displacement?
Energy. Work.
Work. Energy. Or, if you want, moment. It's a dual vision, but what is important there is that we have energy. So when we go beyond the elastic limit, something is left there. And that area means that part of the stress has been converted into energy inside the system, because it's not going back to the equilibrium. So for example, if you consider a building, and you're going to shake it by a nice earthquake, not a violent one. If it's going to behave in an elastic way, it's going to be shaken, then the earthquake is going to cease, everything is going back to the equilibrium, everything will be stable back. But if in some part of the system you're going beyond the elastic regime, part of that, like for example creating some small fractures, part of the energy will be left, because we went beyond that part. So, to study the source, in some way we have to go beyond the elastic limit. Maybe in a very simple way. Let's imagine to take a chalk, we apply a stress. Okay, if the stress is gentle, nothing is going to happen there, or if the knob is stable, okay, some sound is going to be produced. But if I use a hammer and I'm going to create a permanent deformation there, okay, fracture. So it's beyond the elastic limit. Now the question that we can try to think about now is, okay, let's imagine that we have a table here. And at the beginning it's intact. Okay, it's nice, I can knock it, nothing is going to happen. But let's imagine that now I'm going to act with a very strong, very intense force, okay? We're going beyond the elastic limit, maybe some permanent deformation line is going to break. Okay, now let's imagine to continue to apply force. The question that we're going to try to answer later today is, okay, once that the system is broken, is it more favorable to create other fractures or to continue sliding on that fracture?
To continue with the...
That's the answer, but why? Maybe it's very, if you use intuition, okay, it's more, from an energetic point of view, it's more favorable to continue sliding there, and that's the answer. That's important for today, okay? So let's try to remember this. Okay, we're not going to open this parenthesis, but please remember that we can open a parenthesis there about rheology. For example, people that is studying materials or material science or material engineering, okay, so that's wave physics until this point here, okay? Now, the limit at which the system is behaving like an elastic material is called yield limit, okay? What's happening beyond, it depends on rheology. So please do remember that temperature, pressure, composition, and time is important there. And, okay, you see, you break the material, then if you continue to apply the forces, something is going to happen there, because tectonics is still active there. So at the beginning of the history, we created a fault, but then tectonics is going to play again. You can imagine like the music machine, like a carillon. I don't know if it's an English word, okay. In any case, you are going to play again. So what about the music? Is it going to be played by new fractures, or we will have sliding on the created fault? That's the question that we have to imagine today. Okay, but yield is an important keyword there. Please do remember that in many cases we may have plastic behavior. So we can have permanent deformation without a fracture. So it could be ductile system, but no earthquake in that case. We're going to have some important geological features there with deformation, but no stick slip. Okay, we are going to have a continuous flow. You can call it also creep if you want. That's not an earthquake. So please do remember rheology. And for example, if you have a plastic behavior, that's important for many systems, not for earthquakes, maybe, but for buildings, for example. So if you're going to work with an engineer for seismic input, for seismic hazard, the engineer could be interested in to study the plastic behavior of a system. And maybe you want plastic behavior. Why? Because it's going to absorb energy. So in many cases, some vulnerability defense systems are using dissipators inside the building. You can put some technical tools that they are going to absorb energy. So going plastic means that you are going to absorb some energy. And according to the different material, you may have different yield strengths here and different places where then fracture is going to occur. So please do remember, rheology could be another chapter to be studied. And again, pressure, temperature, and time, and material, of course. Okay, that's not what we want to study. Please do remember that if we have no stick slip, we may have a sort of a fluid behavior. So that's why rheology actually is studying many different systems like fluids or polymers, something like that. That's interesting. It's not, again, not my cup of tea, but please do remember that material science is dealing with rheology. And also geology, of course. Okay, and that's a slide that we're going to use in one of the last lectures of the course. Why? Because we will add some Newtonian fluid behavior to the Earth to study anelasticity. So it's a simple slide, but it's an important one. Why? Because a fluid is a system that, of course, the restoring forces, like the K of a Hooke's law, they are strong, but not that strong. It's not a solid. It's not a gas, where interaction forces are very weak, okay? So it's intermediate. What does it mean? That it's going to flow. Now, we studied fluids in a very simple way in wave physics, saying, okay, let's consider an ideal fluid. Ideal fluid has no reaction to shear forces. No reaction. You can cut it and you have no reaction. What does it mean? No S waves in fluids. Is that real? Well, it depends. For example, water is pretty much an ideal fluid. But we have some behavior that is reacting to shear forces. How? Well, the most simple fluid that is not ideal is Newtonian. So Newton is again there. And Newton is saying, okay, look, let's consider stress and strain. That's Hooke's law. A linear elastic solid has a line there, stress and strain. An ideal Newtonian fluid has a line there, but not with stress. I mean, with stress, but not with strain, but derivative of strain. So strain rate. It's important. Why? Because we have time there. So again, you have a line, you have a stress, but not strain, but strain dot. So it depends on the rate. And time is entering there. Please do remember that in Hooke's law there is no time. Here it is. It's simple. And the coefficient that is deciding the slope is called viscosity. So an ideal viscous fluid can be called a Newtonian fluid. It's very simple. For people studying rheology, this is a too simple model. It's too much simple. So we have many different behaviors here, not with lines. But for today, and also for the last lecture, one of the last lectures that we're going to discuss, that it will be about the Q, the quality factor of the Earth, we're going to use this model to add some powder to solids, trying to explain anelasticity. So, again, and please do remember the time is here. So you can imagine to have a system and try, and you can imagine to force it in different ways. For example, you can force it at very high frequency. Time is playing the game. Or maybe you can force it very slowly, okay? It will have a different behavior. We will study this for anelasticity. But for today, we can stay in Newtonian fluids. It's a very simple constitutive law. If you want, it's the companion of Hooke's law, but for fluids. A viscous fluid like that will react to shear forces in a very simple way, but it's going to react. Please give a look to these values about viscosity. So you see that, for example, for air and water is pretty much nothing. It's very, very small. That's why water is very similar to an ideal fluid. You can call inviscid fluid, you can call it Pascalian fluid. Very simple. No restoring force for shear forces. And that's why S waves are not going to propagate into the outer core part, into the outer core, okay? Because it's a fluid. But you see that in some cases, viscosity can be very large. So large that actually it could be like a solid. Actually, the lower mantle is a solid. Yeah, of course, S waves are going to propagate there with very large values. But on very long time scales, viscosity is large but not infinite. So it's going to behave like a fluid on very long time scales. That's the duality, the paradox for example, of a mantle. Viscosity is very large, but not infinite. And so, on long time scales, it can behave like a fluid. Now that's another important topic here that you're going to develop with Karim, I guess. Let's remember that to have an earthquake, we need a rheology that is decided by brittle behavior. So it's going to break. Otherwise, we have a flow. That's interesting, but it's not about seismology, because we have no radiation there. So usually, we have a transition that is decided at a given depth, that is decided by many factors, like composition, that's important. For example, the percentage of water is decided there, but of course, pressure, temperature. So we have a transition here where we have, here, you see, a brittle behavior, and we're going to have a slip. That's it. Maybe if we go to larger confining pressures, let's imagine to make a small travel inside the Earth, of course the pressure of the material that is above, here it's becoming larger, temperature is getting larger, so the behavior is going to be different. And maybe on different time scales, the behavior will be like that of a fluid, so plastic behavior. Important for rheology, but not for seismology, because we need this, we need something that is brittle. So that's why, if you do remember, the quantity that I was showing to you, that is going to be the most important quantity in this part of the course, the seismic moment, it will decide magnitude, okay? So the energy released by an earthquake in terms of seismic waves. Here we have three components, as I told you. Mu is this mu. It's trying to characterize the material, how it's reacting to shear forces. So rigidity modulus. Then the area. And this is the amount of slip. Now, what about the area? The area actually is limited by this behavior, because sooner or later, going to some depth, we will have a transition to a ductile behavior. So area cannot increase too much. And that's why in subduction zones, where we have material that is going to be brittle, is going deeper, that's why area can be larger in length and in terms of width. Otherwise, this transition here is limited A. Is in the seismic moment, is going to limit, luckily, also magnitude. Okay, so let's try to think about this. So we have a transition at a given depth. And earthquakes can only occur where we have a brittle behavior. So again, you can imagine to have a material here, and we're going to play some hypothetical experiments later. Let's try to imagine a sample. Let's try to put it in a lab somewhere. We apply confining pressure, and then we decide to exert some stress over it. In some conditions of pressure and temperature, it's going to break. But in some other conditions, it's going to be sheared. So that's why that's important for geology, but not for seismology. The brittle behavior is going to be elastic up to a given limit, then beyond the yield stress, it's going to break. While in other cases, you may have a ductile behavior, so it's going to flow. And that's why you can imagine to have a sample, to apply some forces, and in principle they can be compressive, extensional, or intermediate, like this one, so shear. And for the seismological vision, we have these three kinds of faults. This is what we want to describe. So what we're going to call a reverse fault, a normal fault, or a strike-slip fault. So if you want part of the Apennines, San Andreas fault, and subduction zones. But of course you have the version without earthquakes, but with deformation. And then you have folding, shearing, and stretching and thinning. So now you can imagine that the dynamics are decided by tectonic forces, a material, and how this material reacts in long and short time scales. What we want to study are these kind of systems here, how they radiate energy. So for today, just a very quick vision about dynamics in the sense that now we're going to discuss about forces. But from the next lecture, it will be a nightmare, let me tell you. We're going to write the representation theorem. We will try to manage this kind of systems here, and then we have to say, oh guys, we cannot treat them. We cannot analytically treat them, because they are a discontinuity. How to do that? Well, we're going to represent them. So we will take the thought, okay, goodbye, and we will try to replace it with something that we can handle. We're going to use the concept of body forces. And the end of the story, let me tell you, will be a double couple. It's not an hashtag, but a double couple. That's the end of the story. So maybe during the weekend, you will know that a double couple is representing this. It's a very simple answer to a very complicated problem. But the price to pay for that simple answer is to study the representation theorem. That's for Friday. Okay? So be prepared. Okay. So, that's the very simple scheme of what we want to study. We have a sample. We have a stress, maybe a confining pressure. Could be the lithostatic pressure of a material with some weight. We have a free surface, but then we have material. We have a confining pressure, and then we have tectonic forces. What's going to happen to the system? Well, if the forces are not that strong, it's going to behave elastically. Okay, like that. Okay. What if we are going to apply stronger forces? Okay, the material will try to resist, trying to stay intact, but sooner or later it's going to break. How? Well, with this. It's quite intuitive, so something like that. And we want to study, okay, at which angle that crack is going to form. The answer will be relatively simple. What is important, let me tell you just now, what we are going to study in this course, it's a limit maybe, but it's the most important kind of earthquake mechanism, will be what we are going to call a shear dislocation. What does it mean? Something like that, okay? Not something like that. We're not going to study openings. Of course, if you want to study an explosion, not a bad nuclear explosion, but maybe, for example, a volcanic event, where you have some part that is related to magma there that is going to push. Okay, we will have a possibility, but it's not what we want to study. We want to study tectonic earthquakes. It's a limit, but that's enough. So we're going to use the concept of shear dislocation. No opening. That's important. That's why we want to study this. So a fracture in a material that will be on a small scale, like in this case, but also on a larger scale, will be a fault. Okay. Now, from a microscopic point of view, you can imagine that at the beginning of the stuff here, cracks will begin to form from a microscopic point of view. Then, if you apply confining pressure, you continue to exert. We're trying to do an experiment now. Later, we're going to do another experiment. You can imagine to have a set of samples of a material, could be a rock material. You put into your lab, you apply confining pressure, you exert a force until it's going to break. Okay, good. Then you throw it away and you place a new one. But now you play the same experiment with a stronger compression, confining pressure. We will see that we need a stronger force to break it. Then we break it and we throw it away. Then we place a new one. We apply still a larger confining pressure and we study when it's going to break. We will see that that behavior will be explained by a very simple law. It's going to be called Hamilton's law. But what's going to happen for one sample with a given confining pressure is this. Sooner or later it's going to break. with a slip. At which angle? Well, the practice saying, look, if the principal stress, you do remember what is a stress, right? Speaking to you, I guess that you know what is a stress, and I guess what you studied in other courses. You do remember that, not by definition like the strain tensor, but it can be demonstrated, and I told you in the wave physics, it's symmetric. Does that mean, okay, we can find a reference system for which all the elements are just diagonal? Okay? So we have just 6 independent quantities, just 3 if we sit in the principal reference system. We can compute the sum. It could be positive, compression, negative, so it could be 0. The sum is going to be its trace, it will be an invariant, and so on. Now, if you take now the 3 elements of the principal stresses, you can imagine that you have the largest one. Between those 3, you have the largest one. And maybe it's this one, okay? Okay, the angle of a fracture is going to be 30 degrees nearer to sigma 1. Which ones? Well, nature decides. But in principle, this or this, they are equivalent, just due to the symmetry of a stress tensor. Now the question is, why it's nearer to sigma 1? The answer, in some slides, will appear. It's quite simple. And everything is going to be explained by a line, with a slope and an intercept pair. We are going to call it internal friction and cohesion. Those 2 parameters will decide that fracture. So the end of the story is that from a macroscopic, not microscopic, but from a macroscopic point of view, any material is characterized by 2 variables that are macroscopically characterizing it, and they are properties of the material. Its friction and its cohesion. Of course, they are internally dependent upon temperature and confining pressure. But those 2 parameters will decide pretty much everything. And that's it. Now, if you want to save one law for today, it's this. It's very simple. And the story of this law here goes back to quite a long time ago. Actually, one of the first scientists to study friction laws was Leonardo da Vinci and Galileo Galilei. But the first one to make these things, to put these things in a sort of a law was Coulomb. And that's why the Coulombian style here, or criterion, is still used today, also to study the dynamics of earthquakes. And everything is very simple. Because the Coulomb is saying something that is quite intuitive. You can imagine to play with a surface here. You can imagine to use an angle, to put a weight, and you can study, okay, what is the angle beyond which the weight is going to slide? Well, if no friction, it's 1 degree is enough. But if you have friction, then, okay, it will depend on that coefficient. So coefficient of friction, and that's it. Coefficient of internal friction. But wait a second, because we have the Coulomb criterion is saying, okay, you will have a sort of a shear, because it's going that way. Can you imagine the experiment of high school? So we have a plane here, we have a weight here, and so it's going to slide in this way. So it's going to be a shear. But the shear will depend upon the normal force and the coefficient of friction. That's it. Sigma n stands for the stress that is normal to a surface. Mu here is the coefficient of friction. And you can imagine that it is a line, and that's the angle. C is what I was mentioning as cohesion. And this very simple law here is also telling us what's going to happen is if the material is already broken, because then cohesion will disappear. So C will vanish, and that slope, because that's a line, will fail, because the intercept will be 0. And that's the answer to what we were trying to study before, and that's it. It's called Hamilton's second law, and it's pretty much the same as the Coulomb. Do you have these slides? We have it, okay. It's pretty much the same as Coulomb, but as you see here, C is no more there. So once that material is broken, cohesion is lost. And this is another coefficient of friction. If you want, it's like to study in classical mechanics, okay, the friction of a system that is static first, and then I have to study what is the force necessary to make it slide, and then the force necessary to make it, once that it is sliding, to continue sliding. You can call it kinematic friction or dynamic friction. We have two different coefficients because for inertia it's easier to make it move once it is moving. Well, at the beginning, as you know, when you want to push something that is heavy, well, the beginning is tragic, but once you move it, it's easier. So it's the same intuitive concept here. So actually the friction law, just as seen from a macroscopic point of view, is simple. That's not the end of the story, but for the other part of the story about friction, Karim scores. Okay. Another funny law, why it's funny, because actually while Coulomb and Hamilton, they were studying based on principles, if you want, or very simple experiments, Byerly in the 70s did experiments with samples, so with real rock samples. So he put some numbers here. That's why it's important. So his experiments, and also the later experiments, showed that these two laws are behaving pretty much also in practice. So we can put some numbers there. Now, the bad news. The bad news, so the good news, very simple law, okay? Very simple. You can remember it just drawing this very simple sketch, because that's the line. You know that, for example, the slope of a line is related to the tangent of an angle. Every time that you draw a line in an analytic plot, okay, the slope is related to, okay, derivative, but it's also related to the tangent of the angle that is forming with the x-axis. Okay, that's the angle. So it's very easy to remember that law. Now, what about the bad news? If we want to make it more formal, we have to go back to the definition of stress. And that's why now the bad news are beginning, because we need to do some algebra. But okay, bad news but also good news, because this slide here is coming from your textbook. So we're not doing some exotic things, we're taking a sort of a classical road now. And what we're going to do is just to rewrite the stress definition as we did in the physics course, but with a different perspective. Because now we want to study the stress in order to try to classify fractures. Okay, to make it simpler, let's consider just two components, okay, not three. We know that elastic materials live in 3D. But since we are lazy, I'm lazy, let's stay in 2. We're not missing anything here, just to make the algebra simpler. Okay, now, stress tensor is symmetric. Good. So, if we refer to the principal axis, we're just two components here. Sigma 1 and sigma 2. One will be the largest, the other will be the smallest. God bless you. Salute in Italian. When we have 3 components, okay, one will be the maximum, one will be the smallest, the other will be the intermediate. But in this case, okay. Now, if we move from the principal axis, we have to compute something that is related to the rotation. So, the writing of a stress tensor will depend by the angle that we are forming with respect to the principal axis. After some boring but simple algebra, we can write the generic expression of a stress in a general system that is making an angle theta with the principal axis in this way. So you could say, why should we do this? Well, because, as geologists know, these two expressions can be, how to say, rewritten in a very simple way, with a circle. Because actually, you can divide the sigma prime, that is the stress in a generic system that is making an angle with the principal axis of theta, we can divide them in what is normal and what is shear. In two components, it's easier. How can we make it? Well, the normal to what? Here you see, okay? So, we have two principal axes. If we refer to them, we have just sigma 1 and sigma 2. Good. Then we ask, let's imagine now to consider a system that is rotated respect to the principal ones. How much? Theta. Now we have no more E1 and E2, but we have E1 prime and E2 prime. Good. Now, let's refer to the normal and to the shear, respect to that surface. Okay, we can write it in this way. And the shear, we can write it in this way. And if you make a plot here, you will see the behavior. It's periodic respect to theta. Of course, everything is related to sine and cosines. So, for example, if the angle is 0, we are related to the principal axis. Now, principal axis means sigma 1 and sigma 2. So we have no shear. Please do remember that the off-diagonal terms are related to shear. The diagonal terms are related to normal compression if they are positive, or dilatation if they are negative. Okay? So, when the angle is 0, we have just the normal, of course. It's diagonal. Then we move. We rotate. And now shear is moving from 0, becoming maximum at 45 degrees, where sigma, the normal, is 0. Now all the terms are diagonal. Then we rotate again at 90 degrees. Again, now we are diagonal, but reversed, and so on. So you could say, so what? Who cares about this? Well, there is another way to use the same expressions, is to use a circle. That is called Moore's circle due to Otto Moore. That was the one to formalize this part. So look, sorry. This has to be moved. Otherwise, we cannot see this. Okay. Now, what is this plot? Well, it's a summary of a state of stress on a body. Why? Because here we can put sigma, and tau, that is the shear. Now, let's give a look to this. 2 theta, 2 theta. Cosine, sine. That's the equation of a circle. Of a circle that has a center here. Just the average of sigma 1 and sigma 2. What about the radius? It's related to the difference. And the state of stress can be seen just here. So we know the angle, okay, let's multiply by 2, we have a point, and we can read sigma and tau. So for example, if theta is 0, we have just the normal ones, and 0 tau, and so on. So, Moore's circle is a summary. One warning, I'm a physicist, I'm trying to be a physicist, so I'm not a geologist. But there are two different conventions. For example, this is the convention adopted by Steiner-Warszashi. Why I'm saying this? Because it's negative. Look here. In many cases, you can use the same plot, but in the positive. It's just a matter of convention. Now, what is the natural stress inside the Earth is compressional due to the lithostatic. Now, compressional for geologists, I guess, is positive, and it's quite intuitive. For physicists, it is negative, because it's acting in this direction, not in this direction. It's just a matter of convention. In this case here, as you see, they are less than 0, so you put there, here, okay? In many plots coming from, for example, earthquake geology, something like that, they are put just on the opposites. Just to remember, it's only a matter of convention. Like with the Fourier transform, e to minus I omega t, electric engineers use e to plus I omega t. That's a mess, okay, but just a convention. So what I'm trying to say to you here is that this circle is a summary of a material. Why? Because the center is telling to us the average of sigma 1 and sigma 2, and the radius, the difference. And once you run there, you understand what is the shear force and the normal force in a body, according to the to the axis that you're adopting to study it. So it's a summary. Nothing is new here. It's just a matter of rewriting what we know about stress. So now we have a circle. And so what? What should we do now? Any guess? Well, first hint. I hope that I put this. Do you have this link here in the material that you have just downloaded? There is the link. Okay, good. Let's see if it is working. I'm not sure because I put it 1 year ago. It was a simple but nice animation. Okay. Okay, good. It disappeared. So in 1 year there was a very nice and simple animation about you could rotate zeta and you could see the evolution of the Mohr circle changing sigma 1 and sigma 2. Why it's not there? Okay, I will try to find. 1 year has passed. No, well, less because I used it also at the university. Okay, so you have to use your animation, your imagination. I will try to find a better link to that part. Now, what should we do now is this. We should try to understand how and when a material is going to break. So now let's take the sample. We apply confining pressure, and now the confining pressure is deciding sigma 1, sigma 2, and sigma 3. Okay? Then we could say, okay, who cares? Let's stay stable, and let's stay here. No. The game that we want to play is, for example, okay, now let's try to increase one of the stresses, and let's see when it's going to break. Of course, we can imagine many different experiments. For example, to apply a confining pressure and apply here an axial compression. Or maybe we can imagine to have an axial extension. Now you do understand that the signs and the numbers of sigma 1 and sigma 2 and sigma 3 are changing in these two different configurations. Or another possible experiment that is not important for the Earth is this. So no confining pressure, and you can imagine to take a chalk and to apply a tensile traction and then you study when it's going to break. Actually, the most important for us is this one. And in this case here, if we continue to apply sigma 1 in that direction, so a compression, the system is going to break at an angle of almost 30 degrees towards sigma 1. Look here, because for example, if we apply a tensile extension here with a confining pressure where maybe sigma 1 is the largest, now the fracture is going to be formed with an angle that is pretty much 30 degrees respect to sigma 1. Okay? So different behavior. Now this is what we have to imagine. And we can imagine to perform these experiments with the help of Mohr's circle. Now, the most important one for us is this. But this plot is here just to let you to understand that the Mohr circle will reflect also the experiment that you are playing. For example, here, and now you see how the convention now is different in reverse with respect to the standing session. For example, in this case here, you have just a tensile. That's why you have sigma 3 here, and no sigma 1 and sigma 2. So you take this part here and you apply it inside sigma 3, that is extensional. That's negative for the geological community. Okay? That's one experiment. On the other side here, we have uniaxial, but it's compressional. So now we're playing this game here. Okay? Sigma 1. Actually, the most interesting for us is this. So we apply confining pressure, sigma 2 and sigma 3, and now we begin to push. Now let's imagine to play this experiment. So we decide sigma 2, the confining pressure, and now we begin to push until the system is going to break. And we stop. Okay? It will reach, when it's going to break, it will be decided by sigma 2 and by the sigma 1 that we're applying there. Then we throw it away. We place a new sample, and now we increase sigma 2. And so we're going here, because sigma 2 is larger now. And we apply again sigma 1 until the material is going to break. We will have a set of circles. If we are increasing sigma 2, the circles, the radius will increase, and it will move to the right. And when the material is going to break, we take a snapshot of a circle. Okay, we're going to create an envelope. And that's it. That's the summary for today. Very simple. Because actually, if you imagine to play that game with different samples, with new samples, remember, new intact samples, you decide them as sigma 2, megapascal, for example. Let's remember stress as a unit of pressure, but it is a tensor, but its units are pressure. So you apply this, you decide a confining pressure by your amount, then you begin to apply a sigma 1 until the material is going to break, the first circle. Remember that the radius, the center is decided by the average, and the radius by the difference. Then you break it and you throw it away. You place a new one, but now you increase sigma 2. And the radius will increase because the material is going to break at a larger sigma 1. You throw it away and you play another experiment. What you're going to form is this line. That's the line that was referring to the Coulomb linear expression. Because this is a line. And the slope of the line is characterized by this angle. And that angle is the coefficient of internal friction. Actually, it is the tangent. Tangent of the angle that is the slope is the mu of the coefficient of the Coulomb. And this number here is cohesion. And now, in a very simple, way, you can imagine what's going to happen if you don't throw away the sample, but you take it and you continue to increase the pressure. Cohesion, it's no more there, and the line is falling down. So this is going to 0. What does it mean? It's not necessary to form new fractures, because the material will prefer to slide there. It's more convenient from an energetic point of view. So the two simple laws of Coulomb and Hamilton can be summarized into this very simple experiment. And you have also the answer why this is going nearer to sigma 1. That depends by the slope and the coefficient, as we will see now. So please remember, it's not going to form at 45 degrees. It will be nearer to sigma 1, because that's the line. Remember, this is 2 theta. You see? The slope, that depends on the friction, on average, for Earth materials is related to this degree, to this angle here. 2 theta is 60 degrees, so it's decided by the slope. On average, for Earth materials, it's 60. What does it mean? That it's going to be nearer 30 degrees, because that's 2 theta, to sigma 1. So you have also that answer. But once the material is broken, okay, maybe it's better, it's easier to continue to slide on that surface than to create new ones. And that could be a problem, but please ask Karim, because for example, when you study earthquakes that are occurring on faults, in principle, those faults have been formed with the tectonic stresses a long time ago. So maybe they are no more reflecting the actual state of stress. That's tricky. But luckily, I'm just a seismologist, so I don't want to study tectonics. I'm just studying, I'm joking, of course, but please think about this. So, when an earthquake is occurring on a fault, you could say, okay, that fault, then it's formed by a tectonic stress that is like that. Well, not necessarily, because maybe it has been formed when the tectonic stress was reflecting that part. And now it's better to continue to slide there, okay? So you're not sure that the picture that you're taking is reflecting the actual state of stress, because maybe it has been formed with a different state of stress, just due to that region. Okay, and this was the game. You see these circles? So you apply confining pressure, then you increase sigma 1, and when the material is going to break, game over for that sample. So you have to increase, bang, you throw it away, then you move to a different sigma 2, larger, and you continue to play this game. You will see that you're going to create an envelope. And that's the envelope that is the linear law of a Coulomb law of friction, if you want. Okay, you throw it away, then you continue, bang. Now, this is the very simple version, in the sense that, for example, what's going to happen at larger stresses? Well, the line is no more a line, it's going to be a more complicated curve. But I have no capability to enter into that domain. There is another important issue that is related to this. It's not very important for earth materials, but for earthquakes, but could be important for materials. What's going to happen if you're going to apply a tensile stress? Okay, let's be Griffith criterion here, and this is a piece of a parabolic curve, okay, this part here, that is related to the tensile when the material is going to break. But actually, unless we go to strange volcanic behaviors for tectonic forces, we don't have that part. So what we want to study is this one. Okay, that's number 3, and that's the summary. So you see that actually the Coulomb friction law, that was a line, the slope of the line is related to the tangent of an angle that is reflecting the material, its friction. While the intercept here is related to the cohesion, that is related to the fact that the material is intact. So please do remember that when the material is broken, you throw it away, and the line will fall down. What does it mean? Okay, it will slide earlier. It's not necessary to break it. It's already broken, so let's continue to slide there. You're lowering the energetics, if you want. So it's more convenient. Okay, this is what I was trying to tell to you. Then you can try to perform these materials. There is a branch of rock mechanics. Ask Karim, please. And you can study different confining pressures, different materials, but you see pretty much all of them have this linear feature. It can be summarized so with friction and cohesion. This is what I was telling you, and that's really the summary. If you want to save the slide for today, save this picture because you have the linear Coulomb friction law that is here. You can call it also the Moore envelope. Here you have a Moore circle as a summary of the state of the stress of a body. Now we're just using it to study it when the material is going to fracture, to be broken. And we use it to plot this game here. And remember that here we're going beyond elasticity, because actually when the circle is not reflecting a fracture, it's still elastic. So wave physics, if you want. But then, if we continue to apply that sigma 1, so increasing it, and we are stopping just at the fracture, we are going to the brittle behavior here. So we are beyond elasticity, fracture. And what is also interesting is that, but again, I'm pretty much sure that you're going to discuss this with Karim, if you have the presence of fluids inside the rocks, please remember that a fluid has the capability of exert stress. You can shout in water, if you remember speaking, water. So it may maintain pressure. What does it mean? That actually the center is going toward the origin here. Why? Because we have a component of the pressure inside of the fluid that is trying to go against this. So the net effect is to move the circle towards, so the active sigma 1 is lower. What does it mean? It's going to break earlier because you are moving it there. So the effect of fluids. Not my cup of tea, I'm sorry. Okay, and that's the additional feature that we get here, because as I told you, that's the Coulomb failure envelope for materials with cohesion. If no cohesion, then the line will fall because you have no more it. And what does it mean? That actually now, since the line is lower, the material will break earlier. Actually, it's already broken. So that's why, once you have a fracture here, that's the behavior. All these angles here will, if you have a fault, a fracture, there, the material will try to slide there without creating other lines, okay, other fractures. So pre-existing fracture, that was an important part. And this again is a vision with data. Okay, the data is a little bit scattered here, but this is actually coming about real rock samples at different regimes, as you can see here, for different confining pressures at different values. And this is called Byerly law, where you have a slope that is telling to you what is the typical average coefficient of internal friction of real rock samples. Why we are discussing this? Because, as I told you, today's role is just to have a sort of a flavor of dynamics. But from the next lecture, we will move to kinematics. So we will not ask anymore why a fault is there. We will try to describe it, okay? So for today, just a sort of an introduction to what you're going to discuss better with Karim. And just is an introduction of the actors that we will study from the next lecture. So for today is why they are there, if you want. From the next is, okay, since they are there, how can we study their radiation? That's our topic, okay, in this part. But just to add some flavor of dynamics, please remember that those lines, so the rheological behavior samples, depends by many features. Composition, definitely yes, but also confining pressure. So rheology depends on confining pressure. For example, that's the strain, and that's the differential stress that the material is able to resist. You see it's linear here, then yield, then fracture, then sliding. And you see that these lines here depend on the confining pressure. Larger it is, larger will be the yield. So different depths, in very poor words, will decide different rheologies. So the same material, but if you apply different confining pressure, will change the behavior. Please do remember that rheology is the leader here. And I put also another one, fluid pressure, as you can see. So rheology depends definitely, confining pressure, temperature. I don't remember if I put also the slide of temperature, but also if you have some fluids. You see that the same material is behaving differently if you add a percentage of water. And that's important from a dynamic point of view. Oh yeah, and that's temperature. So you see, colder a material is, differently it will behave. Larger temperature, okay, the linear behavior will cease before, but actually it will try to be plastic. While here, it is evidently brittle. Okay? And that's the summary for today. And you can call it Anderson theory of faulting. So all this mess here to understand a law that Coulomb was establishing centuries ago, okay. From a macroscopic point of view, we can describe it with more circle, with some samples. We have that line, coefficient of internal friction and cohesion, and so on. Now let's try to apply that simple law to the Earth. And now, what about sigma 1, sigma 2, and sigma 3 in the Earth? Okay, we may have different tectonic regimes. For example, in subduction zones, compressional will be the strongest. Maybe at sea rifts or sea ridges, extensional will be the stronger. In some other places, well, maybe this is not going to be the stronger, not this. Maybe the lateral ones, one of the lateral ones will be the stronger, like in San Andreas. But one thing is for sure, and that's one very simple hypothesis of the Anderson theory of faulting, but you will see it's very simple, is that what about the vertical axis? If you do remember, into the wave physics course, we didn't want to describe faults there, but we used one boundary condition. For example, what about a surface in a flat reference system, the Hall space? The top of the world, if you remember, was a free surface, right?
Yes.
In the final lecture, we used a sphere as a free surface because we had a look to the Earth from a global perspective. But it was a free surface, right? What does it mean?
There is no material beyond that, so the wave cannot occur.
You're right. Well, actually, we have air, as we know, since we can breathe, okay? But for a seismologist, air is so thin that we can say it's empty. But we have another consequence. That all the vertical components of stress are zero. If you remember, we said sigma zz is zero, zx is zero, zy is zero, right? Am I right? So definitely, the vertical axis, where shear forces are zero, has to be one of the principal axes. That's the Anderson hypothesis. And so if the vertical is or 1 or 2 or 3, we have just 3 possibilities. And they are these ones. Maybe the vertical is the largest. Sigma 1 is vertical. Good. So we have an extensional regime. We will not have an opening, but the prevailing mechanism will be that of a normal fault. And the angle will be, on average, 30 degrees respect to the vertical, on average. Good. That's one possibility, the largest. The other one is the smallest. So it's sigma 3, and sigma 1 will be this. So we will have something like that, a reverse fault. On average, 30 degrees respect to the horizontal, on average. And the third and last possibility is that the vertical is the intermediate. So it's sigma 2. So 1 and 3 will be horizontal. And if that is the case, we will have what we're going to call a strike slip. So the end of the story, my friends, is very simple. As poor seismologists, not dealing with dynamics, we have to deal with this. Faults that are shear dislocations, or like that, or like that, or like that. And the game is over for dynamics. What is not over is how to describe them. And that will be the painy lecture of the next Friday. But for today, we can relax and summarize everything here. Please do remember that rheology can be much more complicated. Pressure, temperature, composition, and time. Cohesion, coefficient of internal friction, and blah, blah, blah. But actually, we can summarize everything in this. That's the simplest, the easiest, but important road to earthquake dynamics. So tectonic forces will cause these mechanisms. And that's pretty much game over for dynamics, but not for kinematics. But to end this part, it is a nice part, and I'm pretty much sure that for you it will be easier, because I guess now that's your part. The final slides are easier for a geologist. The point would be to establish a convention to name this kind of faults. Actually, what is a fault with the simplest model? It's a plane. Okay? It's not a plane. It's a volume, but one of the dimensions is very tiny compared to the other two. It's not a plane because it will be a surface that is not regular, but on average it's a plane. Like the Earth is a sphere, it's not, but it's an ellipsoid or something like that. Okay, a fault is a plane. Now, how to label a plane? Well, there are two ways. The first one is to give two angles. For example, let's see the next slides, the angle that is formed by the projection of a fault respect to the north, and one is given. The other one will be this. They are called strike and dip. Good, that's the fault. There is another possibility that we are going to use on the next lecture on Friday. A plane in geometry is given by its normal. Again, a normal is nothing else than two angles. It's the same, okay? So the normal, that is a vector, is giving to us the surface. It's the same. But for the geological convention, the fault is given by strike and dip. Good. We are left with another angle. The direction of the motion of what is called the hanging wall respect to what is called the footwall. For example, it could be like that, reverse, could be like that, normal, could be like that, strike. Now the third angle has many names. In my case, in these slides, I think I've used rake angle, okay? Or we can also call it slip angle, because this is the slip, stick, slip. Now the third angle will tell us what is the direction of the relative motion of the two blocks that are forming the fault. So with three angles, game is over, strike, dip and rake. There is one additional factor, remember, that is inside what I will call the slip vector. The amount of slip, because I can slip for 1 centimeter or for 1 meter, as you have seen for the Toku case. But actually, what is left is just to give names to these angles. And this is the role also of a field geologist. Most of the faults are not visible, they're called blind faults. But in some cases, like the San Andreas fault, they are very much visible. So you can go there with the compass, and you can give some names to the angles. For example, the angle that the line of the surface of the projection of the line is formed with respect to the north. That's called strike. It's between 0 and 360. The other one is dip. It's between 0 and 90 degrees. And the third, as I told you, is slip. So that's the strike. Easy. That's the dip. Easy. It's not that easy, but okay. And the third, and the most important, is related to the slip. That's the real earthquake. Look, a fault could be not active, so you can draw a strike and a dip, but maybe no slip. Slip is the earthquake. Okay? And the slip is given, as I told you, by at least two components. The first is the angle, and it's a convention. For example, 0 and 180 will be a pure strike slip, left or right. Actually, left or right. 90 degrees will be reverse. 270 will be normal, or whatever angle. Please do remember that the slip is not only an angle, but also an amplitude. And that amplitude is here. So inside the definition of a moment, of a seismic moment that will decide the magnitude, the amount of slip is there. And as I told you, look, those brackets means it's an average. Why? Because the reality is not with just one point that is slipping. We have a surface that is slipping with an heterogeneous slip field. And we will try to describe that mess. But in a very simple vision, strike, dip, rake, that is the slip. And the game is over. Of course, you can decide to assign a point to a source. It's not a point. It's much more complicated. But if you want to use a point, okay, the projection is called epicenter. The focal depth is called the hypocenter. But remember that the source is not a point. But if you want, you can draw these things. And so that's a matter of terminology. Now, for the next Friday, are we? Yeah, we have perfectly time. This is what we have to describe. And we will leave the dynamics. Dynamics means, okay, let's try to understand why this is going to occur. Because we have tectonic forces, we have brittle material, we have to study pressure, temperature, the friction law, okay? No, come in. But what we have to do since the next lecture is try to understand how to describe this. I know this picture is not that nice, but it's important because it has pretty much everything. So what we can imagine here is that we have a fault, that the geologist has mapped. So we have a strike, we have a dip, and wait a second, on that plane, a rupture will initiate somewhere. It will propagate, it will stop. That's the earthquake. Now, these fronts of rupture are not fronts of waves. If you want, it's a stress wave. But it's not the wave that we're going to record. The wave will be generated by the slip in any point here, and they are going to be radiated by this. This is the seismic radiator. What is the most difficult part? Well, you see that in general, you can use your intuition, that in general here, these arrows are not the same. They are not in a point. The slip field is heterogeneous. Maybe you have a prevailing direction here, but maybe it's a mess. And not necessarily the largest arrow will be at the beginning of the rupture. Not necessarily, as you have seen in Tohoku, for example. So, rupture is initiating, waves are beginning to be radiated there, so the first P waves will arrive from this point. But not necessarily is the point where the largest radiation occurred, because maybe the largest arrow is here. And it's pointing in that direction. But maybe in other places, it's pointing in another direction. That's why, at the end, when we will take the final step, and we will say, okay, that's a mess. Let's imagine that we are so far that all the radiation can be imagined in just one point. Then we will make an average of that field, and we will get this. And when we can assume that the source is a point, then we can say, okay, let's forget this mess. Let's place there not a fault, but an equivalent system of body forces. The answer will be a double couple. So this mess here can be represented, if you are so far from the source, by a double couple. That will lead us to the plot of what we are going to call focal mechanism, the beautiful beach balls. So the beach ball is a very nice and impressive shortcut that will tell us strike deep and rake. But please do remember that it can be drawn only if you consider a point source that is a representation of this. Okay? That's why from the next lecture we will try to start from this model and try to work it, because it's not easy. It's not easy. Because we have discontinuities there. We don't have volume discontinuities. We don't want to study explosions. We could do that later, but when we will define the moment tensor. We want to study a shear dislocation. Why? Because it's the dislocation that is related to a tectonic earthquake. Okay? So also today's lecture was a sort of introduction, just to plot a frame where we're going to play the movie of a kinematics. But in very simple words, okay, we have dynamics, tectonics, we have materials, rheology, we have fractures, we have cohesion, friction, stuff like that, we have slip. This is what we have to study from the next lecture. Okay? It will be not easy. Yes?
How can we measure those because hidden inside the earth, so we can't access them directly.
Good question. Oh, well, for a fault that is appearing at the surface, you can ask Earth. I don't know if you're a field geologist, I'm joking. But, okay, any geologist is doing some field work where maybe you can map faults. But the question is, okay, most of the faults are not visible. How to do that? I will tell you, and you will do it. But later. There is no answer yet. The answer will be that, according to the seismic wave field that we can detect, we can study strike, dip, and rake. Okay? This is what we have to do. That's why what we did in wave physics will help us. Because we will use, it's like to, okay, let's imagine that we are listening to music and we want to say, okay, who is the man or the woman that is playing the instrument? We will try to understand that just listening to the music. Those are the seismic waves. So let's imagine that we are listening to the radio and we want to study the person that was playing that music. We will try to do that. So the answer, very rough, but it's not, but for today is enough, studying seismic waves. We will have a way to decide that given a seismic wave field, well, the source is like that, with strike, dip, and rake. Okay? It will not be easy, but we will try to do it.
Well, if we use seismic reflection, for example, if we interpreted the cross-section, the seismic cross-section, we can
Okay, okay. Well, if you, okay, she is suggesting another thing. Okay, look, that's a sort of a passive study, in the sense that, for example, you can do applied geophysics and applied geophysics experiment. What is the difference between applied geophysics and seismology? The source. Seismologists are using usually seismic sources. Applied geophysics are using artificial sources. So actually, yeah, that's another. But remember, penetration depth is not that much. So what you can do is to perform an applied geophysics experiment with some explosion or vibro-size or other instruments, and you can study a profile, for example. And then you can see what you can interpret as faults. But not necessarily they are active faults. They can be paleo faults. So you can see the lineaments, but not necessarily they are active, because a seismology is saying, okay, that is active because actually you are using the music played by that fault. In that case, you are trying to study the instrument player, not listening to the music that he or she is producing, but listening to echo of something else. That's applied geophysics. In the case of seismology, we will use the waves radiated by the source. The answer is seismic waves, also in applied geophysics. It will not be easy, but in principle it will be, in principle.
And the other question is how water or fluid content inside a rock, is it decreasing the confining pressure or increasing the confining pressure?
Well, actually it's decreasing the differential stress. So if it is dry, sigma 1 is one value. If it is not dry, the difference between the internal pressure, because it's acting like that, and this, the differential will be less. So the radius will be less. Of a small circle will move. So given this line, it is like if it's moving here, so it will touch the line before. So I am not able to draw it. The very important question is how to study the presence of fluids there. It's not easy. For artificial fluids, in principle it is, because you know, and how to say, human seismology, or that is very famous now in Oklahoma, for example, fluid injection in the underground can excite, can more easily trigger earthquakes. That's anthropic seismology, if you want. The very important question is, what about the nature of fluids that are there at a given depth? It's not easy because we cannot go there and study. Some Japanese teams are studying drilling faults at very large depths, like something like some kilometers inside. But I don't know, I don't have a better answer. You can ask Karina. But induced seismicity with fluids is a proof. For example, you can go to a magnitude, you will see what is magnitude, but up to magnitude 5 earthquakes that are actually induced, so they are triggered by the fluid injection by human activities, for example. But they cannot trigger very large pumps, we hope. But let's see. Okay, my friends, see you on Friday. Be ready for a terrible lecture. Terrible also for me. Just let me tell you one very frank word. You will see on Friday that, oh, let me stop.